determining the acceleration of an object that's moving in 2 dimensions. The first problem is going to be one taken from Tippers, which I've modified slightly to be a little bit more interesting. So it says we have a car on an oval track that is traveling clockwise around the track, and for about half of the track it's traveling at a constant speed, and for the other half of the track it is speeding up. And there are 6 points here, and we're asked to give the direction of the velocity and the acceleration at each point. We have this little direction wheel with arrows labeled A through H, and we can also give J if we think there is no direction for one of those quantities. All right, so this is really going to focus on acceleration, so I'll just fill in the velocity values first. The velocity vector should always be tangent to the path at each of those points. So starting from point R, the velocity would be in direction C, and then D and E. And when we get to U, we're in direction G, and then H, and then A. Okay, so what I really want to focus on is the acceleration. When you're thinking about acceleration in 2 dimensions, it helps to think about the components as being along axes that are parallel to the velocity in what we call the tangential direction, and perpendicular to the velocity, which we call the radial direction. So at point R, the object is traveling at a constant speed on a straight portion of the track. There will be no tangential acceleration if the speed of the object is constant. So that's the effect of tangential acceleration, is to change only the speed. And the effect of the radial, or you might call it centripetal acceleration, acceleration that is perpendicular to the velocity, that will have the effect of changing the direction of the object. So at point R, neither the speed or the direction of the object is changing, so there would be no acceleration at that point, so we would put J. At point S, however, the car is not changing speed, but it is changing direction. So there will be no tangential component to the acceleration, but there will be a radial component perpendicular to the velocity. So at S, the direction of the velocity was D, so acceleration perpendicular to the velocity puts us in either direction B or F. Which one of those 2 directions depends on which way the object is turning. The car is turning sort of to its right, so the acceleration will be in the direction F. Similarly, at point T, the car is in the process of changing direction, so there's going to be an acceleration with a component perpendicular to the velocity, but again, there's going to be no component parallel to the velocity because the speed is constant. So the direction of the acceleration at point T would be G. Okay, now for the second half of the track, things get a little more interesting. Now the speed of the car is increasing. So at all 3 of the points U, V, and W, there's going to be a tangential component to the acceleration which is in the same direction as the velocity. But if the direction is changing, then there will additionally be a radial component as well. At point U, there is no change in direction, so the acceleration will only affect the speed, so the acceleration will be in the same direction as the velocity, which is direction G. Now at point V, now we have a case finally where both the speed and the direction are changing. So the direction of the velocity at point V is h. So that means there's going to be a component to the acceleration in that same direction to cause the speed to increase, but there will also be a perpendicular component, which would be in direction B, that causes the direction to change. So the combination of those two puts us in direction A. And then likewise at point W, the velocity now is in the direction of A. Since there's going to be an increase in speed and a change in direction, we have some acceleration directed in the direction of A, but also some acceleration directed in the direction C. So the net acceleration will be the vector sum of A and C, which puts us in direction B. Okay, so sort of to summarize here, there are 2 components to our acceleration. We have what we might call radial acceleration, which is parallel to the velocity and which changes the speed of our object. There can also be tangential acceleration, which is perpendicular to the velocity, and that causes a change in the direction of the object. Okay, so the second example is from a calculus-based physics text workbook, and it asks you to think about a pendulum that is swinging back and forth, and there are 5 different positions labeled. 1 and 5 are the endpoints of the swing, so that is where the pendulum momentarily stops to turn around. And you're asked to label the acceleration components, AR for the radial acceleration and A sub t for tangential acceleration at each point, and then to label the total acceleration vector in red. All right, so let's just go through and look at the radial acceleration first. So now we actually have to know something about how to quantify radial acceleration. So the magnitude of the radial acceleration of an object will be equal to the square of the speed of the object divided by the radius of its path. In this case, the pendulum is swinging along a circular arc, so r does not change, but v will be changing as it swings. V will be momentarily 0 at points 1 and 5, and it will be a maximum at point 3. So that means the magnitude of the radial acceleration will also be 0 at points 1 and 5, and then it will increase to a maximum at point 3. The direction of the radial acceleration is radially inward, so it's going to be along the string of the pendulum in each case. Okay, so at points 1 and 5, again, we have the radial acceleration equal to 0. At points 2 and 4, the pendulum will have some speed, so there will be some radial acceleration in those directions. And then at point 3, the pendulum will have its maximum speed, so it should have its maximum radial acceleration at that point. Okay, so we have this component of acceleration pointing up towards the pivot of the pendulum that sort of increases as the pendulum gains speed and then decreases back to 0. For the tangential acceleration, that is going to be related to how quickly the pendulum is gaining speed. Now, at this point in the curriculum where this exercise shows up, forces have not been discussed yet, but we can make just a purely mathematical argument here. We know that the speed of the pendulum is maximum at point 3. So from a calculus standpoint, anytime you're at a maximum value, its rate of change is 0. So the rate of change of the speed of the pendulum is actually 0 at point 3, so there would be no tangential acceleration. And then at the endpoints here, we would have the greatest rate of change of the speed. So that means the tangential acceleration also always point tangent to the path, so be something like this at points 1 and 5, and it's going to point in the direction of the increase in velocity. So it's going to be sort of in the direction that the pendulum will be moving as it leaves those points. And then at 2 and 4, if the pendulum is swinging left to right, then at point 2 it's going to be gaining speed. So the tangential acceleration will be in this direction. And at point 4, it will be losing speed. So it will be moving to the right. The acceleration will be in the opposite direction to its motion, which will be in this direction. And notice this still applies when the pendulum is swinging back right to left. Then at point 4, the pendulum will be swinging to the left and gaining speed, so the acceleration is again to the left generally. And then at point 2, the pendulum will be swinging to the left and slowing down, so the acceleration will still point to the right. So these arrows are correct regardless of which way the pendulum happens to be swinging. Right, and so those are our tangential acceleration vectors. And then for the total acceleration, we simply have to add together the 2 components that we've drawn. At 3 of the 5 points, one of the components is 0, so our red vector is just going to overlap whichever vector is non-zero. So we'll just sort of draw it side by side here. And then at points 2 and 4, those are the only points where we have some non-zero acceleration in both directions. So we simply want the vector sum of the two components. So the total acceleration is going to be off in some direction like this. All right, so when you first learn about acceleration of objects moving along a circle, you may just learn that the acceleration is centripetal acceleration, which is towards the center. Here we just have to keep in mind that that is really only true for what we call uniform circular motion, meaning motion at a constant speed. For something like a pendulum where the speed is not constant, the acceleration can vary in direction. So there will always be some component pointing towards the center of the circle if the object has any non-zero speed, but there can also be a tangential component as well. So you can get an acceleration that points really in any direction between purely tangent to the path and purely towards the center of the path. All right, that should be it for those two problems. Thank you for watching.